Hey guys, welcome back. We're going to be continuing our study of random variables. This time we'll be looking at continuous random variables, and specifically the men's 4x100 medley, which is a swimming event. So just a bit of review of what we talked about yesterday with shifting and scaling. When we looked at rolling a dice, there are 6 possible outcomes. Each one of the probabilities of the outcomes are exactly the same. They're all 1 out of 6, right? So we could either get a 1, 2, all the way up to a 6. If we want to find the expected value, or like the average outcome, that would be taking the sum of the outcomes times their respective probabilities, which we looked at yesterday, which would be basically 21 divided by 6, which was 3.5. And now if we want to find the variation, we have to find first the deviations from the 3.5, which was our mean. Deviations is how far each one deviates from the mean. So the observation minus the mean, which would give us 2.5, 1.5, and then a half. And on the other side, we're going to have the same things, but this time they're going to be positive values, positive deviations, because they were more than what we expected. So now, whenever we take those deviations, even the negative ones, when we square them, they're still going to become positive. Anyway, adding all that together will give us 17.5 divided by 6, which is 2.9. So a dice has a standard deviation of 2.9. So over here, our mean, or the expected value, was 3.5. Our sigma, which is our standard deviation, would be, or sigma of x is how it's often shown in the calculator, would be 1.7. And then whenever we square that, that'll give us our total variation, which was 2.9. So, or sorry, that was 2.9 as our variation. We take the square root of the variation, that gives us the standard deviation. All right, then we talked about shifting. So if I took our distribution and I added 2 to each whatever our outcome was, then that would move or shift the entire it would shift the entire event, the entire distribution, to the right 2. And so our expected value, our mean, is now going to be 2 higher, which would be 5.5. But if you notice, the spread of the distribution remained exactly the same. It's the same spread, just shifted over. So our measurements of spread, like variation and standard deviation, remain unchanged. So with the expected value, whenever we add or subtract a constant to our expected value, it's just the expected value plus or minus that constant. So the shifting just kind of pulls it out, and we just simply add or subtract it to whatever the expected value of event was. But whenever we add or subtract a constant to the variation remains the same, so therefore the standard deviation remains the same as well. Now when we're scaling, say we multiply everything by 2, so our lowest value is 2, our highest value is 12, and it's all the even numbers. Now everything just gets spread out by our scale factor. In this case it was 2. So what's going to happen is our lowest value is going to be and our highest value, their range is going to be twice as much as well. Their spread will be doubled. The standard deviation, would be doubled. And the expected value is just going to be multiplied by that constant as well. So 3.5 times 2 would give us 7. Then when it comes to our standard deviation, that's just going to be doubled as well because it's in the standard units. So that would be a times the standard deviation of whatever x was. And then for variation, because variation is in the units squared, because our deviations are now going to be twice as far apart. And then when we square our deviations, it's now going to be our k squared times the variation. So when we take the square root of this, it'll take us back to a times the standard deviation. So nothing too big there. And then what about adding or subtracting 2 random variables? So this is not the same as doubling it. Remember, our probabilities were a triangular distribution whenever we added 2 random variables together. We saw that we just added the expected values of the first one plus the second one, which gave us 7. The standard deviation was not simply doubled, it's less than that, but our variation was doubled, or we just added the variations from each event. So whatever variation we have in the outcome of event A, which is our first dice, plus the variation we have in the second independent event, which is event B, which would be our second dice. So anyway, we add those variations together to give us 5.8. And then when we take the square root of the sum of the variations, it's similar to the Pythagorean theorem. In fact, it's called the Pythagorean theorem of statistics, and that's how we find the standard deviation of the sum or difference of 2 random variables. Now, if we thought about this, instead of adding the dice together, if we would have subtracted the dice, then what we would have expected would be a center of 0. We expect the difference between the 2 dice to be 0. So like the first dice minus the second one, right? So that would be, in this case, would be 6 minus 1, which is 5. If we did another one, then it would be 1 minus 6, which is now negative 5, right? And in fact, those would be the 2 extreme values that we could have, anywhere from negative 5 to positive 5. If we did another one, 5 minus 4 would be positive 1, right? And the most common that we would expect would actually be, oh, another negative 5, would actually be 0. So this whole thing would be exactly the same. It just this time would be centered at 0 and would go all the way from negative 5, which is off the page, to positive 5 here. So the spread is still exactly the same. The expected value is the only thing that would change. We'd subtract the 2. 3.5 minus 3.5 would be 0. But the standard deviation and the variation is exactly the same because it's the same distribution as we had when we added them together, except now when we subtract them, the center is going to be shifted over to 0 because we expect the difference between the two dice to be 0. Okay, so kind of cool. So the sum or difference of two random events, if we just take one dice, it's unimodal, right? The probabilities is 1/6, which is about 0.16 repeating. So for each dice, the probabilities are just as likely. But once we take the sum of two dice, that's where the triangular distribution comes in. It even has a name. The sum of three dice, whoa, that's starting to look like something we've seen before. Or sum of four dice, which is kind of like taking larger and larger samples, central limit theorem kicking in. That's starting to look like a bell curve, isn't it? You know, where we can take something and we have like a normal model where we have the mean and then the standard deviation or the sigma. Oops, let me try that again. The mean and the standard deviation, which is the sigma. There we go. So that's basically our normal model, which is actually going to come into play here whenever we look at continuous random variables. So the sum of two dice, the only way to get a sum of 2 is with snake eyes. There are 2 ways to get a 3, 3 ways to get a 4. The most common is a 7. There are 6 ways to get that, and then back down to 12. And you see the probabilities over here. This is called the triangular distribution. It's kind of cool. So what we do is whenever we have two independent events, we add the variation of the two, which is like taking the standard length of the standard deviation and squaring it. Okay? So you're adding those areas or standard deviation squared, which is really the Pythagorean theorem. So if we can just add the variations from event A, like dice A, plus the variation of event B, the second dice, to get the total of the variation of the two, which is the sum or the difference of the two, then we would, if we started out with just standard deviations, we would square them, add them together, and then take the square root when we're done. That'll get us back to the standard deviation, just in standard units, just as we would with the Pythagorean theorem. So just like the Pythagorean theorem requires us to be a right triangle, for Pythagorean theorem of statistics, it requires the events to be independent of each other, meaning if one event happens, it doesn't change the likelihood of the next one. All right, so continuous random variables occur whenever we have repeated measurements of the same thing. So like head diameter, waist size or something like that, or height, but not weight because that would be skewed, right? So we do have to be careful. There's some things, I suppose waist size could be skewed as well. The weight of newborn babies, that would probably be skewed right towards the left from those that were born premature and stuff like that. So all the things we talked about in the first unit still applying here, and anytime we take repeated measurements of the same thing, most often it's going to become normally distributed, where the mean with some standard deviation can be modeled by a bell curve, which is nice. So everything we know about z-scores, which is the observation minus the mean divided by the standard deviations, that comes into play as well, and we can use the normal CDF cumulative density function as well to find the probabilities of certain events occurring, which is what we're going to do today. But in order to use those models, remember it has to be unimodal and symmetric. So the mode is the ones that's most often. So this one has one mode. It's like one clear peak. So that's unimodal. This one would be bimodal. That happens often when we're observing differences between heterogeneous groups like men and women or children and adults or something like that. You'll see differences that come into play there. Multimodal can occur. It's kind of cool when there's multiple modes. And then something that looks more or less uniform, just like rolling one dice, would be what we call uniform. So not only uniform, but it also has, or unimodal, it also has to be symmetrical. So if it's skewed to the left or skewed to the right, then we can't use it unless we have a large enough sample. Then the central limit theorem will actually make it, the sampling distribution model is normal, which is cool, but we'll get into that later. That's where this is all going though. So then continuous random variables are, unlike discrete random variables where we have a certain set finite number of outcomes and all their probabilities, which together gives us the probability models. Continuous random variables are, we have a mean and a standard deviation, like a bell curve, like a model, and it's continuous. So as you get, you have to have a range of values in order to have an outcome from the CDF. So the probabilities of continuous random variables that are normally distributed can be calculated using a normal model and z-scores. So They can take on any numeric value within the interval of values as well. All right, so if we're adding or subtracting random variables, if x and y are independent, then we can use the Pythagorean theorem of statistics. So the sum or difference of two random continuous random variables would be just the same. Would be the sum or the always the sum of the variations. Even when we're subtracting, the variations are still going to be adding, which is an important thing. So even when we subtract, we still add variation. Okay, so there's still variation from the first event and then the added variation of the second event, which means the standard deviations are like the Pythagorean theorem, they're squared and summed. Then we take the square root of it when we're done. And then the expected values are simply added or subtracted. Instead of just being added, they could be subtracted, just like we talked about with subtracting the two dice. So let's look at number 51. So that wasn't too much. A lot of that was review, but still good to go through again. In the 4x100 medley relay event, 4 swimmers swim 100 yards, each using a different stroke. The college team preparing for the conference championship took their times their swimmers have posted and creates a model based on the following assumptions. So the swimmers' performances are independent. We're assuming that, of course, like if one person does really, really well, that might mean that the next people are more likely to do well. If one person sucks and they're obviously out of the race, then maybe people won't try as hard after that. I'm not sure if they're not competitive, but maybe if somebody is outperforming, now you're behind, maybe that makes you more likely to perform your best to try to catch up or something if you have some goal ahead of you, like swimming, competing against somebody. Anyway, each swimmer's time follow a normal model, so that's good. That means if we time somebody doing the backstroke over and over and over again, their average was 50.72. It was normally distributed, so with a standard deviation of 24 seconds. So basically roughly 68% of the time they were plus or minus 24 seconds to their mean and stuff like that, right? The whole empirical rule model kind of showing there. And same thing with the breaststroke, the butterfly, and the freestyle. The means and standard deviations and times are shown in the table over here, which is nice. What are the mean and standard deviation for the relay team's total time in the event? So we have 4 different events, and they're all random events, right? So each time one of the swimmers does one of their strokes and does the swim that swims 100 yards or whatever, that's a random event. So we have the spread and we have their means. So if we want to find the total, what we'd expect on average, what we would do, let me go ahead and pull up my calculator, is we're just going to, so if the mean time, whoa, big calculator. So if the mean, don't do that again. If the mean for each one of these events is given here, then the total average, what we would expect, would just be adding all those together. So 50.72 plus 50.51, or 55.51, that could have been bad, plus 49.43 plus 44.91. Okay, so that gives us a total average of 20.57. So it's a normal model centered at 20.57. Then to find the standard deviations, we don't add the standard deviations, we add their variances, right? The variations from each event is going to add together. But to get to the variation, we have to, whenever we take these values and we square them, we add them together just like the Pythagorean theorem, that gives us a total amount of variation that we have of 21.26. But again, that's the variation. We want to go back to the standard deviation, so I want to take the square root of that, which will give us the standard deviation for our new model. So our new model is centered at the sum of all the means, because we're adding all the events together, not subtracting. And then our standard deviation, we'll just say is 0.46. All right, so here's our model in all of its glory. So here we have the mean with the standard deviation of 0.46. So I went ahead and just added the 0.46 to each standard deviation. Same thing here. Also, if you remember on our model, the inflection point is going to be the point where it kind of stops curving down and starts curving back up or whatever. So that's this point right here. And that's the measurement of one standard deviation. So you go the same distance to go the second one and a third one. So anyway, good to know. All right, now we want to know the team's best time so far this season was 3 minutes and blah, blah, blah. Well, that's 199.48 seconds. Do you think the team is likely to swim faster than this in the conference championship? Well, the point we're interested in is going to be, let's see, right about here. So just a little bit under 2 standard deviations. Anything more than 2 standard deviations would be considered unusual. That would be in the top 2.5%. But to find the exact percentile, we can use our our normal CDF. So basically, we're trying to find the area under the curve that's left of this. So this would be our upper bound. Our lower bound would be negative infinity. So we want to put this in the calculator. So to do that, we're going to do second variables, and we'll do normal CDF, which is the second option. Our lower limit is going to be negative infinity, essentially. Our upper limit was 199.48. We were centered at 200.57 with a standard deviation of 0.46. Then hit paste. This is going to give you all the information. I basically copied it down over here as well. So this is anytime that you put something in the calculator and you get your answer, which is here, you're going to want to tell them what you put in the calculator if you're taking an AP test. So this is what they want to see, and then you give the output, then we interpret it. So the probability of them given how they're doing in their individual events with their mean and their standard deviations, the consistency of it, the probability that the combined team is going to outperform their best time or whatever is less than 1%. So that would be very unlikely. All right, Mr. Starnes likes sugar in his hot tea. From experience, he needs anywhere from 8.5 to 9 grams of sugar in a cup of hot tea for the drink to taste right. While making his tea one morning, Mr. Starnes adds 4 randomly selected packets of sugar. Suppose the amount of sugar in each of these packets follows a normal distribution with a mean of 2.17 grams and a standard deviation of 0.08 grams. What's the probability that his tea tastes right? So on this one, we're modeling 4 sugar packets. Each one of them had a mean of 2.17. So we're just going to add those together, right? So 2.17 times 4 is going to give us the mean that we're modeling is going to be 8.68. And then our standard deviation, each one of them had a standard deviation of 0.08. And we're going to square that so we get the variation. And then we're going to multiply it times 4 because we want to add the variation of 4 of them, right? And then that's the total amount of variation that would be in the four packets of sugar. So to get back to the standard deviation, I take the square root, which will take me back to 0.16. So basically we have our model here, and we want it to be anywhere from, so centered here with standard deviation 0.16, I went ahead and filled those out. So I want it to be anywhere from 8.5 to 9 grams of sugar. So 9 would be over here. 8.5 would be just under there. And I want to find the area in between those two. That's when it's going to taste right. So basically I need to find the area in between those two. So I want to go anywhere from 8.5 all the way to 9. So my lower limit's 8.5, my upper limit is 9. So let's put that in the calculator. So second variables of distribution, we're doing the second one here. Our lower limit was 8.5, our upper limit was 9. Mean was centered at 8.68 with a standard deviation of 0.16. Okay, cool. Then hit paste and enter. So basically we have an 84.7% chance. So again, show them what you're putting in there, lower limit, upper limit, mean and standard deviation. So that's 8.47. I think that's what I had, right? Yeah, 8.47. So 84.7% chance that the 4 sugar packets will give him the amount, that it won't be not sweet enough or too sweet, which is the 2 areas that we were interested in there. All right, Fred and Leona are friendly. Wow, I read that backwards. Dyslexia is bad. All right, Leona and Fred are friendly. Oh, I must have read it here. That's what I was thinking. Friendly competitors in high school. Both are taking the ACT. They agree that if one of them scores 5 or more points better than the other, the loser will buy the winner pizza. Suppose that they have an equal ability so that their score varies normally with a mean of 24 and a standard deviation of 2. The 2 scores are independent. What's the probability that the scores differ by 5 points or more in either direction? Well, we're looking for the difference between their scores, and we're just going to, you can do Fred minus Leona or Leona minus Fred. It really doesn't matter. Typically, we do the one that we expect to be higher first so that we're dealing with positive values instead of negative values. But if they said they are both of equal value and they're expecting a score of 24, then the difference between the two would be 0. 24 minus 24 is 0. So the expected difference between the two is 0. And even though we're subtracting their scores, the variations are still going to add. So the probability that one of them varies on the high end and one of them varies on the low end is kind of what we're really measuring. They're 2 independent events, so we're going to add the variations of the 2. Well, if they have a standard deviation of 2, then that means they're going to have a variation of 4. Adding those together would be a variation of 8. So all we have to do is take the square root of 8, which is where we get the 2.83 for our model. So our model is centered at 0 with a standard deviation of 2.83 going in both directions. So what we're looking for on this one is the probability that the difference was greater than 5. So either going in the negative direction of 5, meaning that that Leona outscored Fred by 5, because that would be subtracting a larger value, or going in the positive direction for 5, which would mean that Fred outscored Leona's ACT score by 5. So these are the two possibilities. We want to know differ by 5 points in either direction, so we got to add those two together. They're going to be exactly the same because we're centered at 0. They're the same z-scores, just one's positive, one's negative. So when we put this in the calculator, we can't actually calculate two tails at the same time. We could calculate the area in the middle like we did before and subtract it from 1. But I'm just going to go from negative infinity to negative 5, and then I'm going to double that area that I get. So we're going to go to second, variables, normal distribution from negative 999. Make sure you don't use the subtraction key, but rather the negative. They are different. 999, going all the way to negative 9, or negative 5, sorry. We could do the same thing with the positive values if we really wanted to, but let me try this again. So to negative 5, centered at 0 with a standard deviation of 2.83. You could even do the square root of 8 if you wanted to make it exact. Then hit paste, and that's our probability. But the problem is that's the probability for one of them, one of the tails that we calculated. So we need to double it. So take that value times 2, which will give us our real answer, which is 7.73%. So that's a probability that one of them will have to buy the other one pizza. All right, so that's all I've got for you today. If you have any questions, please make sure you let me know. I do apologize on the quiz. So there were two versions of the quiz that I made last year, and there was one I gave before Christmas break, and it was really tough. And whenever I took it, I was like, man, I wrote a really, really hard test. And so I made an easier test, and I had everyone retake it, and we did that in January. And unfortunately, I gave you guys the harder test instead of the easier one. So someone still got a perfect score on it, which is absolutely incredible. So way to go. But the rest of the scores weren't all that great. So if you didn't do as well as you wanted to, don't worry, you're in good company. We can retake it. You can retake the easier one if you want after school, if you can't wait to get your grade back up. Or if we just focus on the test score will replace the quiz score anyway, so I wouldn't worry about it too much, but do make sure you have all of your homework turned in. That would be an easy way to bring your grade up. So if you have any questions, I'll see you later.